Okay, so we're going to jump into the next unit here, Unit 4. This is a unit where we deal with quadratic functions, primarily techniques for solving quadratic equations. Okay, but there's a few other little pieces of it also. So the first thing we're just going to do a skills review today, and I want to go through a couple things with you and maybe reteach a couple things in the way that I'd like you to think about them. Maybe undo a few things you've learned before and replace them with some other things. I don't know. Maybe that's the case. Maybe not. We'll see. The main points we're going to hit, we want to talk about greatest common factor. We're going to look at the difference of squares pattern and then factoring quadratic trinomials. And this should be mostly review, but it's been a while, and so you may be a little rusty. Okay, so first of all, solutions of a quadratic equation. So a quadratic equation is just, what does it mean? Well, it just means we have an equation that involves a quadratic function. Something that could be written in the form ax squared plus bx plus c equals 0. Okay. We'll talk more about solving the equations later. Today we're really just going to focus on factoring. Okay, but we want to make a couple points here. So when we're solving a quadratic equation, the points at which the function intersects the x-axis, those are what we call the solutions. Okay, the solutions are the places where the function intersects the x-axis. Now, there are going to be some cases that we're going to introduce in the fairly near future where we get different kinds of solutions, solutions that involve complex numbers with imaginary parts, where that won't be the case. But we'll talk about that when we get there. For now, we're going to focus on real solutions, which is, real numbers. That's every number you've ever dealt with has been a real number. And so, we'll extend this when we need to, which will be soon. The solutions of a quadratic equation can be called a number of things. We can call them solutions. We can call them zeros, and we'll talk about why that is here in the near future. We could call them roots. Okay, sometimes they're called roots, and then sometimes we just call them x-intercepts. Okay. So the number of solutions to a quadratic equation, number of real solutions, and I want to specify that because we're going to come back again later and we're going to see examples where we have non-real solutions. The number of real solutions simply corresponds to the number of x-intercepts. So if I've got two solutions, that must mean that the parabola corresponding to the graph of our quadratic function intersects the x-axis in two places. We get two x-intercepts. If we have one solution, then that just means that the parabola only intersects the x-axis in one place, so we get one x-intercept. And if we get no real solutions, that would be a case where the parabola does not intersect the x-axis at all. Okay? So real solutions always correspond to x-intercepts. So this is an example of a time when we can use technology to find decimal approximations for the real solutions by simply identifying the x-intercepts graphically. Okay, here's a quick example. I don't want to take time to actually do this right now. We'll have plenty of opportunities later. But here's a little example, right? Like if we had this function f of x equals negative 1/2 x squared plus 3, right? And we want to find the zeros of this function. Well, why do we call them zeros? Because those are the places where the function is equal to 0. So that would just be solutions to the equation negative 1/2 x squared plus 3 equals 0, right? So we want to know, when does this function have a value of 0? If I want to find those things, well, what do? All I have to do is just graph the function and find out where it crosses the x-axis. So those would be my decimal approximations. So why don't we always do that? Well, a lot of times we do in the real world. A lot of times we're okay with decimal approximations. But sometimes we want to have exact answers. And when you want to get exact answers, a graphical method really isn't sufficient, because it's only going to give us decimal answers, and maybe we want to have our answers be exact, so they include square roots and they include fractions and things like that. Okay, so we're going to focus on, and to get exact answers, that means algebra. We're going to use analytical methods. And so that's, of course, what we're going to focus on. Anybody can do this stuff, can type this in a calculator and find the zeros that way. It takes a little more skill to find them analytically. So let's look at one quick example of solving an equation, and this is the last equation that we're going to solve for today. Okay, and then we'll come back to this stuff in the second assignment. I'm going to give you some practice on using the stuff we're talking about today to actually solve some quadratic equations. So how do we solve this? Any suggestions? And there's different ways we could go maybe with this. Anybody want to just either click your mic on or type it in chat? What can I do here to solve this equation? What can I do here? And you can be wrong. Feel free to be wrong, because we're gonna talk about this today, and very soon everyone's gonna know exactly how to do this. But maybe you don't remember well right now. Just throw out an idea, though, somebody.
Would you move the 13x to the left?
To the left? Okay, so I could subtract the 13x. Okay, good. Anybody else have any other ideas?
Divide by x.
Okay, that's what I was hoping to get. Could we divide by x? If I divide both sides by x here, let's just see what happens. X squared equals 13x. Let's go ahead and divide each side by x. And that means I'm canceling those x's. I'm canceling one of those x's. And so that looked pretty easy. I just get x equals 13. Okay, I'm going to go back and try it the other way here too, though. What happens if I subtract the 13x from both sides? I get x squared minus 13x equals 0. Okay, that looks like more work. What do I have to do next? Let's see, Maria, that was your idea. What do I do next?
I don't know. I don't want to just worry better.
Well, I'll tell you what, it seems like everyone's probably thinking, man, I'd rather just divide by x, but there's going to be a problem with that. We're going to lose a solution. And I'll show you why. This is one of the cardinal rules that I want to stress for you guys is when you're solving an equation, you can never divide both sides of the equation by a variable, because when you do, we're going to lose a solution to this equation. We only got one solution, x equals 13, and what we're going to see here is that there actually are two solutions to this equation. 13 is one of them, but there's another one. So here's what we would do on the left side, and it's been a while since you guys have done this, but we're going to factor this. And we're going to discuss this today. We'll get lots of practice. So this is kind of an advanced view of what we're going to be doing today. Does anybody see a greatest common factor that I could factor out of those two terms? Think what a greatest common factor is. The greatest common factor is just the biggest thing that divides evenly into both of the terms. It could be a number or it could be a variable. Factoring out a greatest common factor is exactly the same as undistributing, reversing the distribution process.
X, right?
Okay, so I could undistribute an x, couldn't I? Good. I could undistribute an x, and that's a GCF, greatest common factor. And I'm left with what then? If I undistribute an x, what's my leftover factor?
X minus 13.
Yeah, good. And for now, let's just think about that as undistributing, right? And how would you check to see if it's right? Distribute. If I distributed the x, I would get x squared minus 13x. So it's correct, right? I undid my distribution there. Okay, so now think about this. I've got x times x minus 13 equals 0. Let's do a little warm-up, actually. I feel like we need a little warm-up today. I want you to try to just do this in your head for me, please. Okay, just do this. I'll go slowly, but I want you to do some mental math just to warm up here, all right? Okay, so first thing we're going to do, and I'll even type the steps in chat. That's kind of nice that distance learning has its advantages, I guess. I'm going to type the steps in chat for you. So I want you, let's start with the number 5. And let's go times 6. In your head, you're thinking of a result. Okay. minus 20 divided by 2 times 3.12. Come on, hurry up in your head. Plus 17.1258 times 3.1298. You go with me, everybody? You got this? You should have this stuff now. Come on, times 0. What's my answer? Ah, okay. Yeah. So y'all got it. You kept up. You all had that stuff. No biggie. Okay, there's an important point there, right? An important point. When you multiply something by 0, you get 0. But that's the only way you can multiply two products or two factors and get 0 is if you multiply by 0, right? This is called the zero product property. So I want you to tell me here real quick. If I've got this factored equation up here, right? And let's focus in on this thing. I've got this factored equation, x times x minus 13 equals 0. I've got a product here of two factors, don't I? There are two factors or things that are being multiplied. So we'll call this one factor number 1, and this guy is factor number 2, okay? What's the only way I can multiply two factors and have the product equal 0? I have to be multiplying by 0, right? There's no other way to do it. If I'm going to get 0 for an answer, I have to be multiplying by 0. So what are the possibilities then? Well, there's two things that could be happening here. Either my first factor is equal to 0, or my second factor is equal to 0. That's called the zero product property. So now we'll just find the values of x that make those two things true. Well, there's one solution already. X equals 0, or x minus 13 equals 0 when x equals 13. So look at that. We get two solutions to that, don't we? Not one. There are two solutions, and I'll prove it to you. Let's graph the function in Desmos. There we go. Okay, if I graph this function, let's see, y equals x squared minus 13x, right? Look what happens. Look at that. I get solutions at 0 and 13. Those are my x values, right? Everybody see that? Okay. Or I could do this a different way. I remember we have the other technique is I can graph the left side and graph the right side and set them equal to each other. So even if I did it that way, that's fine. I'll turn this one off. And what if I graph the function y equals x squared and y equals 13x? And once again, if I zoom out far enough on this thing where I can see the intersections, I've got intersections at 0, at x values of 0 and 13, right? I get two solutions, not one. So the moral of the story there, when you're solving an equation, you cannot divide by variables. What you have to do is you have to set the function equal to 0 and then factor and use the zero product property. Okay, if you want to get all solutions, even though it takes a little longer, it's a little inconvenient. It gives you. It's the only way that you're going to get the correct answers. Okay, you can get all the correct answers. And I put a little definition of the zero product property in here just for your notes. So when you're looking back at this, if you have a little bit of extra information. Okay. All right. So now let's focus on the factoring part, right? Because this process of solving by applying the zero product property relies on us factoring whatever is being set equal to 0, right? Because it's not like, it's difficult. If I wanted to find the values of x that add or subtract to 0, well, that's impossible to do in your head, right? I mean, it's, in this case, it works out because our solutions are nice and neat. They're 0 and 13. But what if my solutions were irrational numbers or really complicated fractions? You're not going to be able to sit there and just come up with by guess and check. You're not going to be able to come up with the right values of x that make this term minus this term equals 0. But once I've got it factored, it's a piece of cake, because then we just apply the zero product property, right? So the essential piece of this that we've got to practice is the putting the equation into factored form, okay? And by the way, something else I'll mention here, and I'll say this again, but when I set an equation like this, like a quadratic equation equal to 0, I'm going to define this for you. This is kind of important. So this is what we call a quadratic equation. In this case, it's quadratic. Later on, it won't be quadratic. It'll be something else. In standard form. Okay, where we're setting it equal to 0. So a quadratic equation in standard form in general just looks like this. ax squared plus bx plus c equals 0. And then we'll factor the left side, okay? So factoring. Let's focus on factoring for today. So the process of factoring is when we're going to take an expression, like a trinomial in this case, and we're going to break it apart into a product of factors. Okay, we're trying to write something as a product of factors. That's factoring. Breaking it apart into a product of factors. That's where we're going in this direction, from a sum of terms to a product of factors. Now, if we go the other way, if we're starting with something that's factored and we want to turn it into what we're going to come to call a polynomial soon, which is just a sum of terms, each term has a different power of the variable, well, then that's what we call multiplying or distributing in this case, or in general, we call it expanding. This is usually the word we use in math, is expanding. Okay, when we're multiplying out factors and simplifying. Expanding is easy. Everybody can, that's no big deal at all. Factoring is a little bit tougher. Okay, so what about factoring this polynomial? It's a polynomial just because, and that word's going to pop up a bunch, but don't be intimidated by that. That just means a bunch of terms added together, and each term has a different power of x. Like in this case, the power of x is just x to the 0, but we wouldn't write it, okay? We'll focus on polynomials next unit, on bigger polynomials, bigger than quadratics. Okay, what can I do here? Any ideas how I could factor this? Just someone click your mic on when you're ready to venture an answer here, somebody.
Could you divide by 3?
Okay, I could factor out a 3. Good idea, Adelaide. But instead of dividing this time, when we're factoring it, like if this were, let me show you something here, because Adelaide's idea is a good one. Like if I were solving an equation, 6x cubed plus 9 equals 0, well, then I could just divide each side through by 3, because I'm dividing by a constant. That's always okay to do. I just can't divide by a variable. So if I divided each side by 3, I would get 2x cubed plus 3 equals 0, okay? But if I'm factoring something, I want my answer to be exactly equal to what I started with, just written as a product of factors. So I'm not going to divide by 3. I'm going to undistribute a 3. What's left over if I undistribute a 3? How do I know what goes in here? Well, one way to know, if I'm factoring out a 3, I am literally dividing it away from each of those terms, right? Undistributing means dividing by that, doesn't it? Right? So what is 6x cubed divided by 3? 6 over 3 reduces to what? Somebody?
2x cubed.
Yeah, I get a 2x cubed. Good. And 9 divided by 3 reduces to a 3. Okay. Now, these are equal expressions. If I were to redistribute the 3, I would just get that back, wouldn't I? Okay. So there's an important message here. Always factor out the greatest common factor first if you can. Whenever you're factoring something, even later on when we're factoring great big ugly expressions, your first step is always see if you can factor out a GCF. It always makes things easier and better if you can. Okay. Okay, so here's an important thing also. The greatest common factor is the greatest number and or power of the variables that divides evenly into 2 or more, I should say terms, not expressions. Expressions or terms. Let's just do this. Terms are things that are added or subtracted, right? So the greatest common factors always inherits the sign of the leading term, the term with the biggest power of the variable. So in this case, this is my leading term, right? It's the term that has the biggest power of A. So when I write this in standard form, I always want to write the biggest powers first, right? And if I'm factoring out a greatest common factor, in this case, because the leading term is negative, I'm going to factor out a negative. So how could I write this? What is the greatest common factor this time? What's the number? What's the biggest number that divides into all of those terms?
-4.
Good. It's going to be a -4. And then what's the biggest power of A that I can undistribute? A squared. Yeah. Okay, the biggest power of A that I can factor out, it's always going to be the least common power. The smallest common, like I've got bases here, I've got the base, the variable is A, it's going to be the least common power of whatever the variable is. Okay, so -4A squared, and what's left behind if I do that? I'm going to be dividing -4A squared out of each of these terms. You can either think of it like we did in the last example. You can literally think about it as, what do I get when I divide the GCF away? I divide each term by the GCF. Or, just as good, you can ask yourself, play a little game and just ask yourself, -4A squared times what is equal to -A to the fourth? I think they're equally good ways of doing this. So what's the first term going to be? I'll just ask around a little bit here. Sarah, what's first term going to be?
Would it be 2A squared?
There you go. And the next one?
-4A.
Okay.
And then 1 plus 1.
Okay, plus 1. Good. Okay. Everybody good with that? And once again, remember that I'll make a little note here for you guys on your notes. This is the least common power. Common meaning for A, for the base A. Okay? The smallest power of the variable is what gets factored out. Okay, so let's just get a little practice here. We'll just go through some examples with this one. Let's see, Abby. What am I going to get here? What's my greatest common factor?
Be 4. And then 4x squared.
There you go, 4x squared times some other stuff, right? Okay, let's go ahead and do the other stuff real quick. What am I going to get left over then?
So it would be x squared minus 5x and plus 5.
Plus 5, there you go. Good, okay, good job. Okay, what about this one? Yikes, what about that one? Everybody take a look at that for a second. Okay, what do you think? What's my greatest factor going to be here? Olivia, what do you think? What's the number part going to be? 4. Okay, what about the rest? What do you think? Did you say a squared?
Yeah, a to the power 2, and then also b squared. Yeah.
Okay. Where's that 2 come from?
Oh, I guess it would be 1.
Okay, just a. There you go. Okay, good. Because we're taking the least common powers. So the smallest power of a that occurs in any of these terms is 1, right? Smallest power of b is b squared. So there you go. So that's the greatest common factor. What's left behind from that if I divide that away, Chloe?
Would it be 3a to the third power and b to the fourth?
There you go. Okay.
Minus 2 b to the third.
There you go. Okay, questions on that? Does that make sense? Give me 1 to 5. Okay. How about that one? How many terms are there in that expression? Terms are things that are added or subtracted. Factors are things that are multiplied. How many terms are there in that? Hold fingers up or type it in chat. Okay, I'm seeing some varying answers here. I'm seeing some 2s and some 3s. The answer is 2, right? There are 2 things. Now, you might be thinking, but there's another negative sign. But that negative sign is inside of a product here, right? If I kind of blur my math vision and look from the outside in, I've got this thing. This is a term 1, minus this thing, which is term 2. Right? I've only got one minus sign separating these 2 mathematical things, right? Okay. How many factors are there in this first term? The first thing that's being added or subtracted consists of how many things being multiplied? How many factors are there? Go ahead and just show me fingers, type it in chat. How many things are being multiplied in term 1? What do you think? Yeah. Okay, I'm seeing it. There's 2 things, right? There's 2 factors. I've got m times the quantity n minus 5. Now, n minus 5, inside that factor, I've got 2 terms, right? But on a bigger scale, if we zoom out, so to speak, I've got this first term minus this second term. Okay, so I got 2 terms. Now we want to see, is there a common factor? Is there something that I can undistribute here? This is a tricky looking one. Is there a factor that is the same in both of those 2 terms? Anybody see one?
Would it be n minus 5?
Yeah, n minus 5, right? N minus 5 is a factor that's being, in this case, it's being multiplied by 1 in the second term. In the first term, it's being multiplied by m. So I could factor out an n minus 5. Now, what's going to be left behind if I do that? What's left behind from the first term if I undistribute that? Just type it in chat, everybody. What's left behind from the first term after I factor that out? Okay, I'm seeing it. Good. It's going to be an m, isn't it? Right? And the proof is if I distribute, I'm going to get n minus 5 times m, which is what I ended up with, right? What about the second term? Okay, good. Yeah, I just get a minus 1, and it's factored. Okay, everybody see that? Okay, good. Okay, so now let's look at a pattern here. 2 patterns. One of them is a non-pattern. The difference of squares pattern. This is the opposite. When we turn this around, we call this the conjugate product pattern. And we'll look at it both ways during the course of the class. When I multiply, if I've got 2 binomials, they each have the same terms, a and b, but in one case they're being added, in one case they're being subtracted. I call those conjugates. A plus b and a minus b are conjugates. The product of conjugates is always a difference of squares. Well, we're going the other direction. We're factoring. So if I have a difference of squares, it's always going to factor into, if I break it apart into factors, the conjugate product. So a minus b times a plus b. In either order, it doesn't matter the order, right? There is no pattern for a sum of squares. A squared plus b squared doesn't factor. The best we can do is a squared plus b squared. It doesn't break apart. Okay, so let's see if we can use our difference of squares pattern to do some factoring. What about an expression like this, b squared minus 49? My goal is, can I write that as a difference of squares? Can I write it as something squared minus something squared? Because if I can, this is like an a squared, and that's like a b squared. And my answer is just whatever that is. I'm calling a minus b times whatever that is plus whatever that is, a plus b. Well, obviously the first one is just a b, right? That's already written as something squared. What about the second term? 49 is what squared?
7 squared.
7 squared, right? So a is in this case replaced by a b, and b is replaced by a 7, and we just get the answer b minus 7 times b plus 7. Done. Okay? And you remember, give me a 1 to 5 on this. Do you remember doing this? 5 meaning I remember doing this well. 1 meaning I don't remember this at all. Okay. Okay, good. So you had some experience with this. Now, what about this one? So can we fit this to a pattern? Well, if we can fit this to a pattern, look, I've got an x squared there. So clearly the only pattern that we would be able to use here is a difference of squares. Later on, we'll add some different patterns. Next unit, we'll add a sum of cubes and a difference of cubes, 2 other patterns that we use a lot for factoring. But for now, we've only got one. So we've got to be able to write this as something squared minus something squared. What is it? 49 we already know is 7. What about the 16x squared? 16x squared is equal to what quantity? Say it again.
4x.
4x. There you go. Good. It's the quantity 4x squared. So then we'll just follow our pattern, right? A difference of squares factors into the product of the difference times the product of the sum. So there it is. Okay, no biggie. Okay, focus on that one for a second. Everybody take a look at that one. First step, what do you think? Any suggestions? First step.
You could factor out a 3y.
Okay, good. And remember, we always want to try to factor out a greatest common factor first. Okay, good job. So the first thing we can do here is factor out a GCF of 3y, which leaves us with what?
9x squared minus 1.
Okay. And now so we got a GCF out of this. Now we've got this other factor that is quadratic. It's got an x squared in it, right? So we always want to ask ourselves, unless it's linear, right? Unless it has the biggest power of x is a 1, there's a chance we could factor this thing, right? If it's quadratic or bigger, we might be able to factor it. Well, this is a binomial. It's got 2 terms, so we'll see if we can do this with a difference of squares, and we can, can't we? What's this going to break up into? So we've got our greatest common factor out front. What can I break this up into? 9x squared is the same thing as what quantity squared?
Three x.
Good, so I get a 3x squared. 1 is the same as 1 squared. So what's that going to factor into? Liliana, what am I going to get here?
You would get 9. Wait. Oh my god, I confused myself.
So I've got 3x squared minus 1 squared factors into 3.
3x squared?
Not squared, because look, this is like saying a squared minus b squared factors into a minus b times a plus b, right? So there's my a is my 3x squared minus b is 1 squared. So I'm going to get a minus b times a plus b. Does that make sense? Okay. Okay, so there's that one. How about something like that? Now, what are my options here? I got a couple things I could do algebraically. I could expand this out, y minus 7 times y minus 7, and then subtract 64 and get one trinomial and factor that. I can do that using stuff we're going to talk about today, but I don't need to. This is already set up for me to do pretty easily. What do you think? Any ideas here? Carrie? Can we write that as a difference of squares? Something squared minus something squared?
Wouldn't it be in parentheses y minus x?
Y minus 7, you mean?
Yeah, 7. Sorry.
Okay. Minus.
Well, not minus. Wouldn't it be just another parentheses y plus x? Or minus
Well,
x?
okay, so now there's a difference. This is y minus 7 squared is different than y squared minus 7 squared, right? But couldn't this whole thing just be like my a, right? I want to write this as a squared minus b squared. Well, a could just be y minus 7. How could I write 64 as something squared? Okay, yeah, that's just 8 squared, isn't it? Man, I've really got something going on here. So y minus 7 squared minus 8 squared, that's just following our pattern of a squared minus b squared equals, I'll write it the other way this time, a plus b times a minus b. It doesn't matter the order, right? You can either do the sum first or the difference first, doesn't matter. So what's that going to look like then? What's my a? What's the first thing that's being squared here? Carrie?
Y minus 7.
Okay, good. So that's going to be y minus 7 plus what?
8.
8 times y minus 7 minus 8. And I can simplify those. Y minus 7 plus 8 That's just y plus 1. And y minus 7 minus 8 is y minus 15. We got it. Tricky. Okay, what about this one? Tricky. Any suggestions there? I've got two terms being subtracted. So could we conveniently write that as a difference of squares, first of all? Any suggestions? Anybody want to pitch in on that one? What do you think?
They're both squares.
Okay, so I could write 16x to the fourth as what squared?
As 4x squared.
Okay, that makes sense, doesn't it? If I square that out, I'm going to get 16 times x squared. Squared is x to the fourth. Okay, good. Minus,
9.
okay, 9 squared. And so that's going to break apart into 4x squared plus 9 times 4x squared minus 9. Okay, good. Are we done? Are we done? Go ahead, Adelaide.
Couldn't you put them to the fourth?
What do you mean to the...
You could put 2x in parentheses to the fourth and minus, is it 3 to the fourth?
Okay, right. So you're saying we could write this as a difference of fourths, but we don't have a factoring pattern for that is the only problem. We only have a factoring pattern for a difference of squares. So what you said is correct. Okay, well, are we done? Move on to the next one. Ooh, Andrew, you're shaking your head. What's going on?
Can we not get rid of that square by making another factor, like, doing like 2x plus 3, and then,
Yeah, look at this. So look what he's seeing. So now this one we're done with, right? Because remember, there is no sum of squares pattern, right? And so this is a sum of squares, but who cares? We can't factor a sum of squares. But this guy over here, yeah, we could do something with that, couldn't we? We could write this as a difference of squares. So we get 4x squared plus 9 times the quantity 2x squared minus 3 squared, don't we? Right? Now that's a difference of squares, so that we can split up into a plus b times a minus b. And then I've got this quadratic factor out front that's done. It's what we call an irreducible quadratic. We can't factor it anymore, right? It doesn't fit the pattern. But we could get that broken. That's as far as we could break it down. Everybody see that? So when we factor something, it's always implying that we want to factor it completely, as far as we can go, okay? All right. So now let's remind ourselves how we deal with simple quadratic trinomials. When a is equal to 1, it's a piece of cake. Either it factors easily or it doesn't, right? This is where we just want to find what I call magic numbers. We want to find magic numbers that multiply to c and add to b. So this is in the form ax squared plus bx plus c, right? So b is 8 and c is 15. Can you guys come up with magic numbers that work here? Multiply to 15 and add to 8. What are they?
3 and 5.
3 and 5. Right? Those are my magic numbers. So then all I do is I'm just going to create two factors, and the magic numbers are the numbers that are added to x in the two binomial factors. So that's going to be x plus 3 and x plus 5. You guys remember doing that, right? No biggie. So let's factor this one. What are my magic numbers here? What do they have to multiply to? What do they have to multiply to? Andrew Saxton, they have to, magic numbers multiply to what and add to what? Questions for Andrew Saxton. How about you, Rebecca Bercham?
They have to add up to negative 4 and multiply to negative 45.
Okay, good. And we can play a little sign game with this, right? If the two magic numbers multiply to a negative, what's that tell you about the signs of the two numbers? Two numbers multiply to a negative. Anybody? I'm seeing people say one negative, one positive, right? Opposite signs. So if they're one negative, one positive, if they're adding to a negative, which must be the bigger of the two, the negative or the positive? Yeah, the negative, right? Okay, so we know that we're going to get a big negative and a small positive. And what would those be? Somebody say them out loud. I'm over at the board.
-9 and 5.
Positive 5. Okay, good. And we got it, right? So we get x minus 9 times x plus 5. You got the idea. Okay, so now let's move on to harder quadratic trinomials, where a is not equal to 1. Now, you folks, this is where we'll kind of end things up today. How much time we got? Oh, man, we need these longer periods. So I want to get through at least one example. You guys probably did this using, did you use bottoms up or slip and slide to do these? You remember?
Bottoms up was the most familiar, I think.
That's the one you went over? Okay. And I'll remind you how to do that, but I don't like bottoms up because it's not algebraically rigorous. The steps, I kind of classify it as a trick. It works and it's quick, but it's not, the steps don't follow a logical algebraic sequence. So I want to show you a way to do this that's algebraically sound. This is my preferred way. Much of it's the same. We still have to find magic numbers. We're going to factor out a GCF if we can, always, right? And then once we do that, we're going to find magic numbers, call them M and N. They have to multiply to the product of A and C, and they add to B. Okay, and then once we find those magic numbers, we're going to use those to split up the middle term. The BX term, we're going to split up into M plus N. We're going to split the B into M plus N times X, which we can make two separate terms, MX plus NX, and then we'll factor that. We'll make four, we've got four terms, we'll factor by grouping. So let's look at an example. So first of all, how about this one right here? Well, there is no GCF, right? Let's find our magic numbers. A times C, 9 times 4 is equal to 36, right? Okay, B is equal to negative 12. So we need numbers that multiply to 36 and add to negative 12. What would those be? Multiply to positive 36 and add to negative 12.
2 negative 6s.
2 negative 6s. Okay, so my magic numbers, M equals negative 6, N equals negative 6. So that means I'm going to split this middle term. I'm going to write this then as 9x squared minus 6x. I'm going to split this minus 6x. And it doesn't matter which one. Like in this case, they're the same. But what if the magic numbers were different? It makes no difference the order in which you split these things. It'll work either way. Plus 4. Okay, now we're going to factor this by grouping. How do you factor it by grouping? Well, we're just going to split this into two groups. Okay, two groups of 2. In the first group, we're going to factor out the greatest common factor. So what's the greatest common factor of 9x squared minus 6x? 3x. And that's going to leave us with what other binomial factor then? Would everybody agree it's going to be a 3x minus 2? Everybody agree? Okay, the bell just rang. Give me 1 second. So then on the other side, right, on the other side of this, we've got this plus sign in the middle. From the other group, we need to have a common factor. So whatever we have there on the left side, we have to have on the right side also, right? Then we just have to answer the question, what goes out front? So what goes out front? What do I have to factor away from a negative 6x plus 4 to get a common binomial factor? Well, I'd have to factor out a negative 2, wouldn't I? Right? And now look, we've got a common binomial factor. So when I factor out the 3x minus 2, I'm left with a 3x from the first term plus a negative 2 just means a minus 2. And so it's factored. See how that works? That's algebraically rigorous. We'll review next time. I'll review how to do bottoms up or slip and slide, but I hate those because they're a trick. You know, this works. And this is consistent with what we do with bigger polynomials also. So it's something we'll do later. I better let you go. There's an assignment up there. We'll do a few more examples next time. Have a great day. I'm here after school if you need me.